Hello everyone. I'm Kartik Nayak, and today I'm here to talk about our work on forensic support for BFT protocols. In other words, how to detect Byzantine faults if there's a safety violation. So this is joint work with Peiyao, Gerui, Sreeram, and Pramod. So the problem of consensus requires a group of parties or a group of replicas to agree on a value or a sequence of values. So when used in a state machine replication setting, we are trying to imitate an ideal world where there exists a server which is uncorruptible, accepting commands from different clients and executing it on a state machine. So unfortunately, since we do not have such an uncorruptible server, we instead use, in SMR, we use a group of servers that provide you with the same interface as that of such a single non-faulty server. And this property should hold even if some of these servers are faulty. And in the setting that I'm going to talk about today, even if they are Byzantine faulty or the servers behave arbitrarily. So for example, in this over here to the bottom right, the server on the bottom right is Byzantine faulty. So you require two properties to hold in such a setting. So the first property is called safety, which intuitively says nothing bad should happen. In other words, any two non-faulty servers should not learn a different sequence of values. And the second property is called liveness, which says that a value that is proposed by a client will eventually be executed by every non-faulty server. That is, good things happen. So these servers are working and committing values. So there's been a lot of work in this space in consensus, Byzantine agreement, state machine replication, and there's 40 years of research on this topic. The primary focus or a lot of focus has been on designing protocols that can tolerate a large number of faults. So how many faults you can tolerate? So for example, over here in terms of notations, so the tolerance that I'm thinking about, I'm using T to denote it. So T out of N of these parties can be Byzantine. And the focus over here has been to tolerate a large number of faults, and it depends on what faults these are. So if they're crash versus omission versus Byzantine, the number of the fault tolerance that I can have can vary. Again, depending on the network settings as well as cryptographic assumptions I make, again, the fault tolerance vary. So in each of these settings, there has been a lot of focus in consensus protocols to design to tolerate as many faults as possible, and at the same time, achieve good efficiency. And efficiency metrics over here can be latency, communication cost, and so on and so forth. So of course, you have this tolerance threshold T, but the actual number of faults, which I'm denoting over here by F, it can be anywhere in any range. So for all these protocols, when F is less than or equal to T, then these protocols show that you can have safety and liveness. So the question is, what happens when F exceeds T? This is a very relevant question, as Itai did touch upon in his keynote talk, where if I'm using, so when I'm designing these protocols, I know that there is a maximum threshold. But if I deploy this in the wild, I cannot say just because I'm making an assumption, it means that we are not going to have more faults in practice. So ideally, when F is greater than T, you would want some more properties that can help you, that can save you. So of course, safety and or liveness can be violated in the setting. The property that we're looking for is this notion of forensic support. In particular, if there is a safety violation, we want to provide an irrefutable evidence of bad behavior by these Byzantine parties. So if there's a safety violation, hopefully we can detect who they are, and hopefully we can punish them externally. So two obvious questions over here are, is it always possible to detect these bad parties? And second, even if it is possible, what does it take for us to obtain such evidence? So if I view this as a spectrum on the number of Byzantine parties that exist, then when we have too few, we have everything good. We have protocols that are safe and live. On the other hand, if we have too many Byzantine parties, let's say if it exceeds the threshold n minus t, it turns out that we can show that there is no forensic support. And we cannot detect too many of these Byzantine parties. Intuitively, this holds because if there are n minus t Byzantine parties, then actually you have sufficiently Byzantine parties to simulate their own world. And in this simulated world, they can always claim that there are honest parties who are not participating in this protocol. Okay, because of this intuitive reason, which we formalize in our work, we can show that when there are too many Byzantine parties, you cannot get any forensic support. Of course, this is parameterized over here, and over here the parameter of interest is D, or the number of Byzantine replicas that you can hold accountable. Okay, so we have no forensic support for D greater than n minus 2t. For the region in between, you can potentially have forensic support, and in particular, you can potentially detect T plus 1 Byzantine parties. So why is this number T plus 1 over here? So in some sense, T plus 1 is optimal because T plus 1 Byzantine replicas are sufficient to actually cause a safety violation. So even if you have more Byzantine parties, well, they may not actually cause a safety violation. And that is why that's the best you can hope for, is to detect T plus 1 Byzantine parties. So I must say that we are not the first work which talks about forensic support. There have been multiple previous works like peer review, Casper, Polygraph, Grandpa BFT, and so on. In fact, some of these like Casper, Polygraph, Grandpa BFT, they were designed with forensic support in mind. Our goal, on the other hand, is to look at existing protocols and try to analyze them and figure out, what forensic protocol, what forensic support do they already provide. And we think about this based on the following three metrics. So the first metric is how many Byzantine replicas can you detect? So this is denoted by this parameter D, and you want to detect as many Byzantine replicas as you can. A second metric is how many witnesses exist who actually hold a proof that can be used to hold culpability. And finally, the distributedness of this forensic aspect. How many witnesses do I need to reach out to before I can construct an irrefutable evidence? So ideally, you want the number of witnesses and the number of replicas detected to be high, and you want the distributedness or the number of witnesses you need to reach out to be low. So interestingly enough, when we were coming up with this work and we were sharing intermediate results with some of our colleagues, we actually got two different responses from different peers. So one was, this work is very interesting, very relevant, and we did not know this was possible. And a second response was, well, there's this work, Casper, which already does this, and this idea that Casper has generally applies for most or all Byzantine protocols. So we analyzed multiple different protocols, and hopefully the key takeaway that I want to share in this talk is that there are these subtle details that actually matter in terms of whether or not you can get forensic support. And that is what I want to present over here by showing two different protocols which have varying degrees of forensic support. So on this axis, the bottom axis is the number of Byzantine replicas that you hold accountable. So we want this to be high. And the number of witnesses we want to contact should be low. So bottom right is good, top left is bad. And I'm going to show you two protocols with these two extremes. Okay, so this is going to be the focus of the talk today. So let me start off with HotStuff, which is a partially synchronous protocol presented in POD C 2019. So there's a protocol that tolerates 1/3 Byzantine faults. So before talking about forensic support for HotStuff, I will give you a 2-minute primer for what this protocol does. So I'm not going to explain all of the gory details of the protocol. That will take a presentation in itself. So what I will present is perhaps the high-level invariant that needs to hold in this protocol. And for those of you who already know about it, you will still have a riddle a little later. So you can play detective together with me. Okay, so this protocol progresses in a sequence of views. And in each view, there is a designated leader. So what I'm showing to you over here are messages sent in one view. So the leader sends a proposal for a value, and together with it, it will send some additional information that can be used by the replicas. So the replicas, based on this additional information and the proposal that is made and their local state, they can decide whether or not to vote for this value. If sufficiently many replicas vote, that is, if 2t plus 1 replicas vote, then we say a quorum certificate is formed. And the first quorum certificate that is formed is called a prepare QC. So then the leader just takes this prepare QC, shares it with the replicas again, and you have a second round of votes and a third round of votes to eventually form what is called a commit QC. So on observing this commit QC, any replica can commit a value. So the leader will receive this and will share with other replicas as well, so that they can commit as well. So an important step in this process is the last round of vote, where if I commit because I obtain a commit QC, then I have this guarantee from sufficiently many replicas, in particular 2t plus 1 replicas who have performed vote 3. They're responsible now for guarding the safety of my commitment. So essentially, when they do a vote 3, they're actually claiming that, well, we are locked on V and we will not vote differently. And this is what ensures that even in subsequent views, they will always vote for V and only QCs for V will be formed and V will be committed. So essentially, when I vote, I'm making a promise that I will not vote differently. Unfortunately, just this does not suffice. And this has got to do with a liveness constraint. That is, if I vote, I'm making a promise I will not vote on something else. But if no one has committed a value, for liveness reasons, I need to be able to vote on something else. So this constraint needs to be relaxed a little bit, where the promise says, I will not vote differently unless I know it is safe. Okay, so what does it is safe mean? Over here, it means that if your leader in a subsequent view can provide you with the proof that says there is a prepare QC that has been formed in a higher view, this is shared in the form of this HQC along with the proposal, then it is okay for me to vote. Okay, so this proof essentially means that although I did a vote 3, I'm assured that no one has committed a different value. So with this in mind, let us look at one potential attack that is possible in this setting. So of course, all of the claims that I made only hold when f is less than or equal to t. So this attack will assume that f is greater than t, and we have 4 replicas, so there can be 2 Byzantine replicas. So let's say in view E, these 4 replicas, A, B, C, D, 3 of them, A, B, and C, performed a vote 3, because of which a commit QC was formed, and someone committed B. So over here, I'm writing it as party I committed B because it really doesn't matter who commits, because even an external client can commit it based on this commit QC that is formed. So it really doesn't matter who commits. Okay. After this, let's say no other messages were received. No commits happened in the intermediate views. And eventually, a new leader came in. The new leader proposed B prime. And let's say they engaged in a sequence of rounds in this view E prime. And some party J obtained a commit QC for V prime because it received sufficiently many vote 3 messages. And now we have a safety violation. So a question for you, especially the ones who already know HotStuff, is, which of these parties do you think are Byzantine? Observe that in these 3 rounds of votes that happened, different replicas have voted in each of these 3 rounds. Okay, so just to keep it interesting for everyone, let's not maybe chat or mention anything on the chat. Okay, I received a few responses. In the interest of time, perhaps I'll end the poll now. And here are the responses that I received. So overwhelmingly, most of you said it's B and C. There were two who said none of these or do not know, but the rest of them said it's one of the top three. So let us try to go ahead and analyze what's happening over here. So a first thing to observe is that based on the information that I have provided to you, D is not Byzantine. Well, it never made a promise. It never voted a vote 3 for V. So it never made a promise to guard its safety. So based on what you see over here, D is not Byzantine. A second observation that we must make is that vote 2 and vote 3 in VUE prime do not matter, because to perform these votes, all I need is a QC from the previous round of votes, which if obtained, then I can just go ahead. That is sufficient proof for me to do vote 3 and vote 2 and vote 3. So perhaps what matters is the first round of votes in VUE prime, and B and C should be culpable. So my current claim is that B and C are culpable. It turns out that this is not true, at least based on the evidence I have shown to you. The reason is that, remember, I told you earlier that whenever you're shown a proposal, I can vote on a value that I'm locked on, or I can vote on a value if the highest prepared QC shown to me along with the proposal comes from a higher view. And in this case, it can so happen that HQC comes from a higher view than E, in which case it is okay for B and C to vote on this value. And this holds for all views greater than E, except the first higher view where a prepared QC was formed. Okay, so intuitively, we need to identify the first view where this happened after view E. Let us say it's view E star. And in this view, it must be the case that the high QC comes from a view lower than view E. And the parties who voted for this particular proposal must be potentially culprits. So again, how do I identify these culprits? We simply take an intersection of the parties who did a vote 3, who were responsible for guarding the safety of value V. They said, well, we are locked on view V, we are locked on value V in view E. And the parties who did a vote 1 in view E star, which is the first higher view. So over here, they made a contradictory claim, which says we're locked on V prime, or our locks are older than E. Both of these are false. So you can detect culpable replicas. So by the way, in terms of the poll itself, the right answer was, I do not know, because I had not given you sufficient information to say one or the other. So there are two people who got it right. So in terms of, so to detect culpable replicas, I'm just looking at the intersection of the commit QC of the first commit and parties forming the first prepared QC afterwards on a different value. There are still two questions that remain. The first one is, well, who has access to this first prepared QC, because that is required for me to know this latter set. It turns out that this depends on exactly how this execution unfolded. Though if V prime was indeed committed, then sufficiently many honest parties should have it. That is, we will have multiple witnesses. A second and more interesting question is, how do we even know that E star was the first such view? So this is where I'm going to say subtleties and implementation details really, really matter. So in our work, we actually analyze 3 different protocols. And the only change in all of these protocols is the information included with vote 1. And we can show that depending on this information, we can have a protocol where there's a single witness identifying T+1 Byzantine replicas, or we can have a protocol which require multiple different witnesses to construct sufficient evidence, or we can also have a protocol that has no forensic support whatsoever, even if you obtain transcripts from all honest parties. So for details of all of these, please refer to our paper. So with that, let me move on to the second part of the talk. And that is to talk about Algorand BA and make an intuitive claim on why Algorand BA does not have any forensic support. So in the general set of papers on Algorand, there are multiple different protocols that exist. I'm going to talk about one specific binary Byzantine agreement protocol from Sheng and Mikali in 2016. It is a synchronous protocol tolerating 1/3 Byzantine faults. And the protocol actually is fairly simple. So it just runs 3 steps one after the other, and it does so iteratively. So it keeps executing these steps until replicas terminate. So at any point in time, every replica maintains a local binary value B. And this is the value that the replica thinks will be eventually committed. And what I'm showing you over here is the pseudocode corresponding to one of these steps. It looks like a lot, but it is actually fairly simple. So in every step, I will first send my local value to everyone, and then I will simply count the number of votes I receive on any value. If I receive greater than 2t votes on 0, I update B to 0. If I receive greater than 2t votes on 1, I update B to 1. If none of these constraints actually are satisfied, then at the end of the step, I would set B to a value depending on what step of the protocol am I in. Okay, in step 1, I prefer B's value to be 0. In step 2, I prefer B's value to be 1. In step 3, I will toss a common coin. So for our purposes, common coin does not matter, so we'll just ignore it over here. It is related to liveness of the protocol. Moreover, when do I commit? So for step 1, my preferred value was 0. So if I observe greater than 2t votes for 0, then I will terminate. And similarly, I will do the same for step 2 and for value 1. Intuitively, the reason why this protocol works is because when f is less than or equal to t, let's say a party commits a value b equals 0. Okay. At this point, this must have happened in step 1 because that is the only step in which I can commit. It must be the case that all honest parties at the end of the step have value b equals 0. This is because either they receive greater than 2t votes on 0 and they have b equals 0 and they committed, or they picked their preferred value of b equals 0. Okay, so at the end of the step, all honest parties have b equals 0, and eventually, if this constraint holds, then it is the case that you will always hit this first condition on the number of votes being greater than 2t for b equals 0. So they will never change their local value to b equals 1, and a different value will never be committed. So very simple intuition on why this protocol works. However, when f is greater than t, things change. We can have a safety violation. So this condition which says all honest parties will have b equals 0 is still true, but unfortunately, you do not have sufficiently many honest parties. You have less than 2t of them. And what this means is that the states of honest parties depend on what Byzantine parties send. And if they do not end up sending this value 0 in any of these rounds, honest parties can actually switch their local value to b equals 1. And they can end up committing this value 1. Well, you can say that Byzantine parties cheated over here. What if we detect them and call these Byzantine parties who do not send 0 as culpable? Unfortunately, you cannot do that because this world is actually indistinguishable from a different world where where all the parties actually sent 0, but there exist Byzantine parties who received the correct set of values and yet decided to switch their value of B to a 1. And then later they come in and claim, well, we never heard from a certain set of parties. So these two scenarios are indistinguishable from each other just based on the transcripts that you receive from honest parties, because of which we can claim that this particular BA protocol does not have any forensic support. So let me quickly summarize what we have learned over here. So we looked at two different protocols, HotStuff and the BA protocol used in Algorand. We saw that at least one variant of HotStuff has a strong forensic support. And the BA protocol that we discussed from the Sheng paper does not have any forensic support. We did observe that implementation details really do matter in terms of what we can and cannot get. And in our work, we actually talk more about other protocols as well, variants of PBFT and VABA, as well as for DMBFT, which implements the HotStuff protocol, we implement a forensic client in their open sourced repository. And we also show some generic impossibility results on what is and what is not achievable in terms of forensic support for BFT protocols. With that, I'd like to thank you, and I'd be happy to take questions.